There is a scale at which the Earth appears almost motionless. Mountains stand above the landscape. Oceans extend beyond the horizon. Continents seem fixed in place. The ground beneath a city appears solid enough to support everything that has been built upon it. But the apparent stability of the planet is an illusion created by the limits of human perception. The Earth is constantly changing. Some changes occur in seconds. Others require centuries. Some can only be understood across the history of the planet itself. An earthquake releases energy through the crust in moments. A river can take thousands of years to carve a valley. A mountain range may rise over millions. An ocean basin can open and close over geological time. And beneath the surface, the interior of the planet remains in motion. The world we inhabit is not a finished structure. It is a temporary arrangement of energy, matter, water, rock, atmosphere, and life. Every landscape is part of a process. Every continent has a history. Every ocean is moving. Every mountain is being built and dismantled at the same time. The surface of the Earth is not the planet itself. It is the visible boundary between forces operating at radically different scales. From the molten interior to the upper atmosphere, from the deepest ocean trenches to the highest mountain ranges, the planet functions as a system of interacting layers, a system that existed long before humanity, a system that will continue long after the civilization of the present has disappeared. This is the geosphere, not a place, a process. The story of the Earth begins before the planet existed. Around 4.6 billion years ago, the solar system formed from a vast cloud of gas and dust. Gravity drew material together. Particles collided. Larger bodies accumulated more mass and exerted greater gravitational influence. The process was violent. The young solar system was filled with collisions. Fragments of rock and metal repeatedly struck the growing planets. Some were absorbed, others shattered. The Earth itself was assembled through this accumulation of material. As the young planet grew, so did its internal heat. Radioactive decay contributed energy. Collisions released more. The pressure of gravity compressed the planet. The early Earth was not the blue world visible from space today. It was a hot, unstable planet, shaped by impacts and volcanic activity. As the interior remained molten or partially molten, the materials within the planet began to separate according to density. Heavy metals moved towards the center. Lighter silicate materials remained above them. This process created the basic architecture of the Earth: a metallic core, a thick mantle of silicate rock, and above it, a relatively thin outer crust. The structure of the planet is therefore determined by a process that began during its formation. The Earth is layered because gravity separated its materials. The crust is the part of the planet most familiar to us, but in geological terms, it is only a thin outer shell. Beneath the continents, the crust may extend for several tens of kilometers. Beneath the oceans, it is generally much thinner. Compared with the size of the planet, the entire surface on which human civilization exists is remarkably shallow. Almost everything that defines the human world exists within a narrow interface between the solid Earth, the atmosphere, the oceans, and life. The deepest mine ever excavated reaches only a small distance into the crust. The deepest boreholes penetrate only a fraction of the distance towards the center of the planet. Humanity has never directly reached the mantle. We have never physically visited the core. Much of what is known about the Earth's interior comes from indirect evidence. Earthquakes provide one of the most important sources. When seismic waves travel through the planet, they change speed and direction depending on the materials they encounter. Some pass through solids, others cannot travel through liquids. By studying these waves, scientists have reconstructed the internal structure of a world that remains almost entirely inaccessible. The planet beneath our feet is therefore known not through direct observation alone, but through the behavior of energy moving through matter. The interior of the Earth cannot be seen, but it can be measured, and the consequences of its movement are visible across the surface. The crust is not a single continuous shell. It is divided into large tectonic plates. These plates move across the surface of the planet, carried by processes driven by the heat of the Earth's interior. Their movement is slow. Typically, only a few centimeters each year. For a human observer, the motion is invisible. For geology, it is transformative. Where plates move apart, new crust can form. Along the mid-ocean ridges, material rises from the mantle and cools to create new seafloor. Where plates collide, one may be forced beneath another. This process, known as subduction, recycles old crust into the interior of the planet. Elsewhere, continents collide. The Himalayas are the result of one such collision. The Indian plate continues to move northwards into the Eurasian plate. The crust has been compressed, folded, thickened, and forced upwards. The result is a mountain system that reaches higher than any other on Earth. But the same forces that build the mountains also initiate their destruction. Rainfall erodes exposed rock. Rivers carry sediment downwards. Glaciers excavate valleys. Landslides remove entire sections of slopes. The Himalayas are therefore being raised and worn down simultaneously. Construction and erosion are not separate phases. They operate together. This is a recurring pattern across the planet. The forces that create landscapes are constantly opposed by forces that dismantle them. A volcanic eruption may build new land. Wind and water then begin to remove it. A tectonic collision may raise a mountain range. Weathering begins to lower it. A river may deposit sediment in a delta. The sea may redistribute it along the coast. The landscape exists in the interval between these processes. Some of the most dramatic expressions of this planetary activity occur around the Pacific Ocean. The Pacific Ring of Fire contains a vast concentration of active volcanoes and earthquake zones. Here, the movement of tectonic plates produces some of the most powerful geological events on Earth. The surface can remain quiet for decades. Then, in minutes, accumulated energy is released. Cities can be damaged. Coastlines can change. The seabed can move by several meters. The atmosphere can be filled with volcanic material. A geological process that has been operating for millions of years can suddenly become visible within a human lifetime. The Earth does not operate at one speed. That is one of the fundamental challenges of understanding the planet. A process may be almost imperceptible and yet capable of producing immense change. The movement of a plate is slow. The consequences of its movement can be immediate. The Earth is often described as a terrestrial planet. From space, however, it is dominated by water. The oceans cover more than 70% of the surface. They are not separate bodies in the conventional sense. They form one connected system. Water moves between ocean basins through currents, evaporation, precipitation, and the circulation of the atmosphere. The oceans absorb solar energy in the tropics and transport heat across the planet. Their movement influences climate far beyond the coastline. A current can carry warm water towards a colder region. Cold, dense water can sink and travel through the deep ocean. The result is a circulation system that operates across the entire planet. Much of this movement is invisible from the surface. The ocean has a surface world and a deep world. Light penetrates only through the upper layers. Below them, pressure increases and temperatures fall. The deepest trenches extend almost 11 kilometers below the surface. At those depths, the pressure is immense. Yet life exists there. In some environments, ecosystems are sustained not by sunlight, but by chemical energy emerging from the Earth's interior. Hydrothermal vents release hot, mineral-rich fluids into the cold darkness. Microorganisms use chemical reactions to obtain energy. Other organisms depend on them. The existence of these ecosystems demonstrates that life is not restricted to the conditions familiar on land. The oceans also preserve the geological history of the planet. Sediments accumulate on the seafloor. The remains of organisms settle through the water column. Minerals are deposited. Over time, layers build upon layers. The seafloor becomes a record of climate, of biology, of volcanic activity, of the changing chemistry of the ocean. The oceans are also one of the Earth's great climate regulators. They absorb heat. They store carbon. They interact continuously with the atmosphere. A change in the ocean can affect weather patterns across continents. The atmosphere, in turn, changes the ocean. Wind drives currents. Rainfall alters salinity. Temperature affects density. The relationship is continuous. There is no clear boundary where the ocean ends and the atmosphere begins as a planetary system. They are part of the same circulation. The water falling as rain over a continent may have evaporated from the ocean. The heat carried by a current may have been absorbed thousands of kilometers away. The climate of a region is therefore influenced by processes occurring far beyond its boundaries. The planet has changed many times before. Climate has shifted. Ice sheets have advanced and retreated. Sea levels have risen and fallen. Species have disappeared. New forms of life have emerged. Change is not new. What distinguishes the present is the speed and scale at which human activity is altering several planetary systems simultaneously. The industrial economy has transferred carbon from geological storage into the atmosphere. Land use has changed the distribution of forests, grasslands, wetlands, and agricultural systems. The oceans have absorbed much of the additional heat entering the climate system. The Earth is often divided into systems for the purpose of understanding it: the lithosphere, the hydrosphere, the atmosphere, the biosphere, the cryosphere. These divisions are useful, but the planet itself does not operate in separate categories. Rock influences water. Water reshapes rock. The atmosphere drives weather. The oceans absorb and redistribute energy. Life changes the chemistry of the air and the soil. Ice reflects solar energy and reshapes the land. Human civilization interacts with all of them. The Earth is old beyond human imagination. What appears permanent is often only stable within the limits of human perception. A landscape may remain familiar for generations and still be changing continuously. A civilization may seem immense and still occupy only a brief interval in geological time. The planet does not move according to the rhythm of human history. Its processes are slower in some places, faster in others. But they are continuous. The surface is rebuilt, eroded, buried, lifted, flooded, frozen, melted, occupied, abandoned, and rebuilt again. Humanity has become capable of changing the conditions of its own environment. That capacity is recent. The systems on which civilization depends are not. They began long before us. They will continue after us. The question is whether human societies can understand the structure of the planet well enough to live within its limits, adapt to its changes, and recognize the forces that have always shaped the world beneath them. Because the Earth is not a stage on which history takes place. It is part of the history. The air, the water, the rock, the ice, the living world, the energy moving through them, all are connected, and beneath the apparent stillness of the surface, the planet continues to change. Slowly, continuously, completely. This is the geosphere, the world beneath the world we know.